In this video, we're going to be looking at this problem, evaluate reverse Polish notation. We're asked to evaluate an arithmetic expression, but instead of being represented in the conventional notation, it's represented in a different format called reverse Polish notation. We're also given that the only operators in this expression are going to be addition, subtraction, multiplication, and division. And division is going to be integer division. And we're guaranteed that the expression is valid and there's no division by zero. Okay. Let's start off by breaking down this question. So first, what's the difference between conventional, aka infix notation, and reverse Polish notation? With infix notation, we would have something like this, 1 plus 2 times 3. Essentially, we evaluate this expression by reading it from left to right, but to compute it, we have to follow the order of operations. So multiplication and division go first, then addition and subtraction. So first we do 2 times 3, which is 6. Then 1 plus 6 is 7. So this seems simple enough since this is basic arithmetic that you probably would have learned in elementary school. But the issue with infix notation is that we have ambiguity if we don't also include parentheses. So for example, consider 1 minus 2 times 3. Depending on where we put the parentheses, we get a different result. If we put them around 1 and 2, we get 1 minus 2, which is negative 1, times 3, which is negative 3. If we put them around 2 and 3, we get 1 minus 2 times 3 is 6, so 1 minus 6 is negative 5. The use of parentheses adds a layer of complexity to the expression. If you think briefly about how a program might parse and evaluate an infix notation expression, it's actually quite complicated with a lot of edge cases. Now let's look at reverse Polish notation. In this format, the operators follow their operands. It's easy to see its rules by looking at a few examples. So instead of 1 plus 2, we have 1, 2 plus. What this tells us is that we see 1, then 2, then once we see the plus operator, we apply it on the previous two numbers. This equals 3. Let's look at the example in the problem, which is 2, 1, plus 3 multiply. We see 2, 1, then plus, which is an operator. So we replace this with 1 plus 2, which is 3. Then we see a 3, then multiply, which is an operator. So we replace this with 3 times 3, which is 9. And the answer is 9. And then the other example that they give is 4, 13, 5, divide plus. So we see 4, then 13, then 5, then divide, which is an operator. So we look at the last two numbers, which is 13 and 5. So 13 divided by 5 is 2 by integer division. Then we see a plus, which is an operator, so we do 4 plus 2, which is 6, and the answer is 6. So try a few examples on your own to convince yourself that using reverse Polish notation, all expressions are unambiguous and there's no need for parentheses. Let's think about the algorithm that we're applying here. We're looking at numbers until we see an operator. Once we see an operator, we replace the last two numbers with the result of applying that operation. And then we repeat this process until we're left with a single result. So the pseudocode would look something like this. So for each token, if the token is a number, well, we're going to continue to the next token. If the token is an operator, let's call it x, we want to replace the last two tokens, let's call them a and b, with a, x, b, where x is plus, minus, multiply, or divide. So let's think about how we might want to implement this, using the pseudocode as a guide. We're iterating through each token. When we encounter an operator, we need a way to retrieve the last two tokens. So if we do some kind of brute force approach in place on the array, you might think at first, okay, so if we're at index I and it's an operator, we can look at index I minus 1 and I minus 2. But then the issue is that when we try to replace the last two items, in this case, once we reach the plus, we want to replace 2 and 1 with 3. We have to remove them from the array, and then we're going to essentially end up with gaps in the array. So after this, we're going to end up with 3 here. Then we see the 3, and then once we see the multiply, we're going to look at I minus 1. Okay, so then that's the 3. But then we still have to iterate through the array, the length of the array, until we find the next number. Try some more complicated examples for yourself and you'll quickly convince yourself that this is pretty tedious. It's also lots of edge cases. Time complexity wise, we're looking at O n squared. So one loop to iterate through each item. Then for every operator we encounter, you have to iterate backwards the length of the array. Let's try to take a different approach. So we don't actually care how many numbers we encounter in a row. We only care when we encounter an operator. And even then, we only need to retrieve the last two numbers. Specifically, we need to remove the last two numbers and replace it with the result applying that operation. We can achieve this with a stack. Recall that a stack lets you push items to the top. To retrieve items, you can only pop items off the stack starting from the top in LIFO order, last in, first out, and this is exactly what we need. We'll push numbers on the stack, and only once we encounter an operator do we push off the last two items, perform the operation, then push the result onto the stack again. So let's see this in action. So first we see the 2, we push it onto the stack. Then we see the 1, we push onto the stack. Then we see the plus, since that's an operator, we pop off the last two items, we do 1 plus 2, which is 3, then we push 3 onto the stack. We see the 3, that's a number we put on the stack. Then we see the multiply, which is an operation, so we pop off the last two items, do 3 times 3, which is 9, then push 9 onto the stack. And then the remaining item on the stack is the answer, so we return 9. In terms of time complexity, we have one loop that iterates through the input, so that's on, and then at each iteration, we either push onto the stack if it's a number, which is o1, and if it's an operator, we pop off the last two items, which is o1, perform the operation, which is o1, and then push the result back onto the stack, which is also o1. So essentially the time complexity here is on. In terms of space, well, we're only pushing numbers onto the stack. In every reverse Polish notation expression, if it has x numbers, there will be exactly x minus 1 operators. So since for every two numbers we need an operator. So about half, or n over 2 of the terms are numbers, the rest are operators. Which means that we push at most n over 2 numbers onto the stack in the worst case. So the space complexity is also on. Alright, let's jump into the code, and we're going to be implementing this in Java. Okay, we're going to start off by importing the stack class from java.util. And we're going to instantiate a stack of integers since we're only pushing numbers onto the stack. There's lots of different ways that you can check if the token is an operator. You can probably make your own function where you check if the token equals plus, minus, asterisk, or backslash. In this case, we're just going to make a string called operators, and then we're going to check if this string contains that token. So then we're going to iterate over each token. The first case is if the token is an operator. So then that's if the operator contains the token. And then the other case is, well, if it's not an operator, it has to be a number. And we already know what we're going to do with numbers, which is we're just going to push the token onto the stack. So since the token is a string, we need to parse it into an integer. In the operator case, we're going to pop off the last two values from the stack. Let's make a switch case here so that we can do different logic based off of whether it's a plus, minus, etc. So if it's a plus, we know that the result is going to be, we're going to add up the last two items from the stack. If it's a minus, then we're going to do second minus first. Times, we're going to do second times first. And then if it's a divide, we're going to do second divided by first. So keep in mind, since this is Java and we're using integers, this is going to be integer division. Then as we said, we're going to be pushing the result onto the stack. Now at this point we know that the remaining item on the stack is the result, so we're going to return it. Alright, so let's run this code. And you'll see that it passes. So yeah, that's how you do the evaluate reverse Polish notation question.